Introduction to redox. So redox comes from the word reduction and oxidation, and it treats all reactions as if they are a transfer of electrons, as if everything is ionic. And it does so that we can understand what's happening in the reaction. So it's tracking the transfer of electrons. Reduction is the reaction in which the substance gains electrons. The overall oxidation state is reduced, and that's where the word reduction comes from. Oxidation is the reaction in which the substance loses electrons, and the overall oxidation state increases. So just like when we were looking at Bronsted-Lowry acid-base reactions in which it involved a transfer of proton, this involves transfer of an electron or electrons. And just like with the Bronsted-Lowry acid and base, you had to have something that was giving the electrons and something that was receiving something, right? So you need to have both reactions occurring at the same time, which is why we call them redox reactions. It's not just reduction, it's not just oxidation. So there are two mnemonics that go with this. You can either say Leo goes Gur, in which losing electrons is oxidation, or gaining electrons is reduction, or oil rig. Oil oxidation is loss and rig is reduction is gain. Either of those will help you remember that even though it feels counterintuitive, that reduction is a gain in electrons. So as I said before, electrons don't float around. They have to be transferred from something to another. So what is oxidized is going to give the electrons away, and that which is reduced is going to grab that electron. So I'm looking at the reaction of lithium and fluorine becoming lithium fluoride. So notice that I'm not worried about right now making this into a diatomic element. I'm just trying to show the transfer of electrons. So lithium, because it has a low Z effective, is going to lose the electron. Lithium will be oxidized. And fluorine has a high Z effective. It will gain the electron and it will become reduced. So lithium is oxidized and transfers its electron to fluorine. And fluorine is reduced and causes lithium to be oxidized. So what is oxidized is the reducing agent. What is reduced is the oxidizing agent. The reducing agent is a bit of a stretch. So when fluorine is reduced, it's because it's grabbing the electron away from lithium. So it's easy to see that fluorine is the oxidizing agent. Calling lithium the reducing agent of fluorine makes it sound like it's forcing fluorine to take the electron from it. I think they're just trying to be fair. So one thing that we keep talking about is oxidation states, and it's a method of keeping track of with what is oxidized and what is reduced. So we first have to figure out how to figure out the oxidation state of any element. So rule is fluorine, when it's in a compound, is always -1. Halogens are always -1 unless they're with fluorine. Fluorine always wins. Oxygen is almost always -2. Alkali metals are +1. Alkaline earth metals are +2. The oxidation states of everything add up to the overall charges, and hydrogen is usually +1. It can sometimes be -1, but usually +1. So let's look at some examples. So here I have the dichromate ion. The overall charge of the dichromate ion is -2. So all the oxidation states within this polyatomic ion have to add up to -2. Oxygen's oxidation state is almost always -2, so we're going to assume it's -2. Each oxygen has an oxidation state of -2. I have 7 of them, so the overall oxidation state that oxygen brings in the dichromate ion, all 7 of them, is -14. That means the 2 chromiums have to have an overall oxidation state of 12 because the 2 chromiums oxidation state plus the -14 that the oxygens are bringing have to equal the overall -2 right here. So the 2 chromiums together have to have an oxidation state of +12. Each chromium has an oxidation state of +6. So when we talk about oxidation states within a compound, we're talking about the oxidation state of each element by itself, not the 7 oxygens and the 2 chromiums, but each oxygen and each chromium. So each oxygen has an oxidation state of -2. Each chromium has an oxidation state of +6. Here's another example. There is an I3 -1 ion. This means that the overall oxidation state is -1. All 3 of these iodines have to sum up to -1. So the overall oxidation state of iodine is negative 1/3. So this just to drive home the point that this isn't just like an actual transfer of electrons at this point. Really, we're doing this to keep track of what's going on. So oxidation states are, in some ways, a relative measure of the Z effective of an atom or an ion. And so iodine can have a partial, a fractional charge to it. Then if I'm looking at N and H in the molecule N2H4, hydrogen will have an oxidation state of +1. There are 4 of them. That's the subscript. So the total oxidation contribution of hydrogen is +4. There is no charge, so the overall oxidation states have to add up to 0. So that means that this N2 part has to be -4, because -4 plus +4 equals 0. So if both nitrogens have a contribution of -4, and there are 2 of them, each nitrogen has an oxidation state of -2. Nitrogen's -2, hydrogen is +1.